Hi everyone, and thank you for attending today's webinar. My name is Lorena James, and I am an application engineer focusing on electrical system design and harness engineering. Today we will talk about how to automatically generate accurate harness costs and work instructions. First off, if any of you have any questions, please feel free to post them in the chat box and we will address them at the end of the webinar. As far as audio, you can choose to use your computer audio or you can dial in using a phone. From this point, I will be muting everyone in order to prevent any background noise from coming up. This webinar is hosted by Oasis Sales. We have been a premier EDA partner with Mentor Graphics, a Siemens business, for over 20 years. If you have any questions or would like more information on any of our other software solutions, please feel free to reach out to me and I would be happy to help. Oasis provides a total solution for enterprise-level EDA and cabling solutions. We will be discussing tools for wire harness design and manufacture, which Oasis is known across the industries as the leading implementation expert. We provide 3 solutions for wire harness design. If you attended our previous webinar, it focused on our capital solution and more specifically, our Harness XE application. Today's webinar will focus on 2 other applications in the capital suite, TVM and Workbooks. We will begin by discussing why the wire harness industry is on the search for new technologies. Then we will discuss Capital's model-based manufacturing approach using TVM and Workbooks. Then I want to highlight the success story of a wire harness manufacturer in the Midwest. And we will follow with a demo and a quick summary. The wire harness industry is an important and growing industry. Challenges within the industry such as increased competition and complexity and demand for lower prices and turnaround time have caused executives to seek technologies that will transform their engineering costing and ultimately manufacturing efficiency. Wire harness assembly is largely a manual process and the design data is often re-entered. This leads to design changes not quickly and adequately synced to the manufacturing, which results in rework and scrap. Rather than spending time optimizing their process, harness manufacturers end up fighting it. There are various people who need to know the cost of a harness. Very early on, costing engineers need to know in order to quote it, and industrial engineers are interested in minimizing build costs and how to plan an efficient assembly process. So what do people use today? Excel macros are homegrown applications that have been built over the years. The problem with these is that they tend to be closed systems that do not respond to change well. And if you have different processes, it is difficult to change these and update to the most current use. Oftentimes they are hard-coded, which then limits the number of processes that can be costed, leaving no time to optimize. Capital TVM, or Total Value Management, decomposes the harness design against manufacturing process models to automatically create a manufacturing scheme for each harness, resulting in a structured bill of materials. A structured bill of materials, or an SBOM, reflects the sequential process of building the harness. It is also composed of each of the associated tasks that need to be completed to build the harness, and each of their associated costs, including time and labor rates. It allows you to take the same harness and run it through different processes to see the difference you get out of these manufacturing processes, which could represent different manufacturing facilities. If that's the case, then TVM allows you to optimize cost and resource allocations across multiple manufacturing sites. It also allows for full reuse of facility models and output formats, minimizing maintenance overhead. And like the rest of the Capital Suite tools, it is available through the API in order to extract whatever format you would like or whatever information is needed to bring into your ERP system. Today it is difficult and time-consuming to create work instructions. A lot of the time, the design data does not flow directly into the creation of them. Thus, they are created in a separate tool that requires manual re-entry of data. As we know, manual data entry is more prone to error, and an error found in the testing stage could result in rework and scrap. Another issue with today's work instructions, or lack of, is the risk associated with tribal knowledge. This is information and methods that are in people's heads and not documented. They can potentially take this with them if they decide to leave the company. Capital Workbooks automatically generates operator work instructions by mapping a digital description of the harness design against the production process model, or pattern as we call it. One or more pages can be generated for each step of the harness assembly sequence. For example, splicing, connector loading, wire twisting, and these include tables, static images, conditional images, barcodes, etc. Essentially, each of the operations is tagged with a workbook template, which is highly configurable through the use of providers or Java apps that pull the harness information into its map destination on the template. These provide rich controlled output formats that conform to quality standards, minimize training needs, and reduce the likelihood of misinterpretation by production staff. Since they are generated automatically, they eliminate errors and minimize costs of manufacturing documentation creation. They can be generated in HTML and PDF outputs, which allow for a flexible delivery of work instructions to the production floor. Currently, the templates are configured in an HTML format, but the new Capital 2019 release will include a new graphical interface that will make it a lot easier to configure the templates. A success story I want to highlight is that of the Central Group, which is actually the company I used to work for prior to Oasis. Prior to adopting Capital, the harness and quoting manufacturing process was very manual, to say the least. The quoting process itself would take about 10 to 12 days, and even after winning the business, it would be several weeks before the start of production. After adopting Capital, the quoting process went from 10 to 12 days to about 2 to 3. The initial Capital process has better prepared us for the start of production with automatic generation of work instructions, specifically splice charts and connector insertion charts that were previously created manually using tools like Visio. TVM allowed for the consistency of quotes to improve. Quoting was done on a spreadsheet that was very detailed prior to Capital, but if two engineers used the same sheet, they would still come up with different costs. Workbooks allowed the visual aids that were being provided to the production floor to be provided more quickly, consistently, and of much better quality. They no longer had to wait for these visual aids to be completed in order to start production or in order to move on to a revision if there were revision changes implemented. Today, Central runs a fully automated quoting and work instruction generation process. Now we will move on to a live look at the Capital tools. So I want to start by highlighting what the input to TVM is. So I want to take a look at this harness design, which is what we will be running through the pattern. First off, we want to start off with a complete harness. So you can see that this is complete. We have obviously bundle structures, connectors, wires, some ring terminals, some insulation. And if you attended our previous webinar, you know that this orange check mark identifies that the component is associated to a library component. So we have a complete harness. We want to make sure it is fully processed, that we have the most current links, most current components. So I'm going to actually go ahead and reprocess. Go ahead and save. And I'm doing this in case, say, a bundle length changed or a connector was replaced. Then we would need to know the new wire and multi-core lengths, especially if the bundle length changed, whatever wires and multi-cores run through that. Any mandatory components that might be associated with the new connector that we might have replaced. We'll go ahead and run that. I want to ensure that it is a complete harness, nothing is missing, so I'm going to go ahead and run our DRC. Again, this will check for something like empty bundles, missing components, missing terminals, and we get two errors, and that is that the power 1 and ground 4 wires have no strip length at connector blunt 1. So if I hover over to that connector, I can see that that is a blunt connector, so I actually don't want to, or a blunt connector identifying that these are blunt wires, they don't need to be stripped. So I am okay with that error. And again, what I'm looking at right here is actually the form board design of, the form board diagram of this design. If you recall from our previous webinar, this can be automatically generated from a not to scale, so this is sort of like a freehand or even imported MCAD structure of the bundles. And the form board is just as generated from the not to scale, and one can go ahead and add the bends, the arcs to make it fit inside of the sheet that it's going to be built on, and add any fixtures that might be needed. So I haven't added any fixtures, but electrically component-wise, this is a complete harness. So I'm going to go ahead and move on to our TVM application. So first off, I want to highlight the SBOM, right? So I referenced that in the presentation, and the SBOM is a hierarchy of operations that it takes to build the harness. Thus, it creates subassemblies, and these are consumed until ultimately they all fall under one operation. So you can see here that my final operation is final inspection and shipping. If I go ahead and expand that, I have all of the other operations that it took to get up to that point, and these are themselves subassemblies composed of subassemblies underneath them. And to highlight that, I wanted to pull up the design, and I have it dimmed. So if I select a subassembly, which this is the cutting of wire W1, it'll highlight where that wire, or it'll highlight that wire and trace it along the diagram. So with that said, we're going to move on to the pattern building interface. So like I said before, you could have multiple patterns that could possibly identify different manufacturing sites or just even different manufacturing processes within one facility. So a pattern is built off of operations. So operations are tailored for the specific process that is going to be occurring in them. For example, we have here an operation template for process single wire. So this template would take in parameters that apply to wires. Here we see a minimum and maximum CSA, minimum and maximum length. You can identify the sort of process that's going to happen at the wire end. So you're going to just strip it and terminate it, or strip, terminate, and seal it. This differs, for example, from a preload connector operation, where you would put in information on how you want the connector loaded with the wires, and what kind of subassemblies can be preloaded into this connector. So, as we mentioned, it's a hierarchical process. So once a wire is cut and terminated, that in itself becomes a subassembly, and all the way down to, for example, splice subassemblies. So once it is spliced and a spliced component is consumed, the whole thing becomes a subassembly, and you could filter that out if you wanted to at the preloading stage for a connector. And this is where you would do that. So operations are made up of tasks. Tasks identify the specific task or steps that need to occur in order for the operation to be complete. These are structured to identify the component or subassembly that they apply to. So for example, here we have a task to auto-cut a wire. It applies to a wire, whereas a strip wire end applies to a wire end, adding the terminal to a terminal. Now, within the task itself, you can apply it to a wire, but you can query further to identify a specific gauge range of wires like I have here. And so then you could possibly have multiple tasks for the different gauge ranges. So the task and the matching object identify what kind of component will be consumed, and the formula identifies the time it takes to complete this task. And here you can get as granular as you would like. You can see here, in order to cut these wires, it is filtered by the length, or the time it takes to cut the wire depends on the length of the wire. So if it's less than 1,000 millimeters, it will take 0.041 minutes in order to cut that wire. If it's greater than 20,000, it'll take 0.348 minutes. So these again are highly configurable, and you can get as granular as you would like with these formulas. As you can see, in order to build a pattern, one must understand the process that it takes to build a harness. For example, you need to understand the kind of equipment that you're working with. For example, cutting machines, you need to understand if it's a cutting machine that can only cut and strip, if it's a cutting machine that can cut, strip, and terminate. Same with the termination operations, right? You need to understand, if you have different cells, if you're equipped with the different bench tops or applicators that you need in those specific cells, or if you need to use a hand crimp tool. Something like twisting wires, right? You need to understand where in the process that is going to occur. Something like splicing, there's different kinds of splices, and these splices can also be interconnected that then come together and build a daisy chain. You need to understand when and where that occurs in the process. And ultimately, all of these sub-assemblies need to come together into some type of a form board. And we need to identify the order that things are going to be laid up on the form board. One other thing, we can use tasks to account for the setup costs or setup time needed to set up machinery, to set up the bench presses. You know, how long is it going to take to change spools of wire? How many different kinds of wire are you using, and how many spools are you going to be changing for your cutting machine? So we talked about the tasks and the formulas. You can further break down the pattern or add more information to the pattern by assigning cost centers and resources. So again, you can have your cost center library and resources. You could assign it to your separate departments, right? Wire cutting department, terminating department, form board department, and assign your different resources. So perhaps a machine operator is paid more than an assembly operator, so then your different labor rates would be accounted for there in order to get an accurate cost for your whole harness build. So we can review the hierarchy of the SBOM within the pattern, but we can also get outputs that we can then feed into our different systems, for example, our ERP system. So something like a cost center report, which only shows the specific cost center and the time it takes, the time spent in that cost center to build that specific harness. This can then be fed into the ERP system that will probably break it down and assign different work instructions or whatnot. So this is one pattern that I'm looking at right now. We reviewed during the presentation that you can compare and contrast different processes in order to optimize and figure out where it would be best to build a specific harness. We can access TVM analysis and comparison in order to view this. So here we can see just the breakdown, the cost breakdown for one pattern, one manufacturing site. I can go ahead and add a compare and compare it to a different manufacturing site. And I can add more than one. So here we see the breakdown by cost center, and we can see a more detailed view, a more detailed table in this cost center tab. So in here, actually, my demo pattern has different cost centers assigned than my TVM pattern 0 and TVM pattern 1. But in this tab, you can see the delta. So it is quicker by 0.1 minutes, right? By 0.1 minutes to cut the wire for that same harness in pattern 1 rather than pattern 0. And so by seeing this graphically and even numerically, it is easier to see, you know, where it would be best to build the harness. For example, you could be comparing a pattern that's for a process in Mexico and one for the States. So in Mexico, you might have a more manual process, but the labor rates are a lot less than they would be in the States. So even though you have a lot more automation in the States, it might still be more cost effective to build it outside of the country. So with that said, we're going to move on to our workbook application. And as you can see, the interface is the same. We still have the same harness design, and we're still running it through several patterns. And the only difference is, at least in the editing pattern interface, is the addition of this workbook template tab. In here, you could assign one or more workbook templates to a specific operation, and so then anytime that a component runs through or something makes that operation fire, then this template will show. And so you can configure these or scope these either by subassembly, operation, or workstation. So for example, the cutting wires operation is scoped to operation rather than subassembly. So this means that I am going to get a list of all of the subassemblies that run through this operation, and that will be my output, as opposed to having it scoped to a per subassembly, where I would get essentially a page per wire per subassembly. If we dig into the code behind it, like I said, it is like an HTML format, and what brings in the information is these providers. Like I said before, in the new 2019 release, it'll be a much more GUI interface, so the user will be able to drag and drop the providers wherever they want them placed within the template, be able to turn them on, turn them off, and handle parameters or turn on, turn off parameters right on the interface rather than having to type them out. So now that we took a look a little bit of the backbones of the workbooks, as far as generating, right, it is just essentially a button click, and you can generate a PDF or HTML format. I actually did go ahead and generate one already, so I'm going to go ahead and pull that up. So you can see that this is that operation that was scoped to an operation as opposed to a subassembly. So it is listing all of the subassemblies that are going through that operation. You can see all the different providers kicking in and bringing in the different images for the different kinds of components inside of the design. So you can see here, obviously, it's a multi-core, and it identifies the names of the inner cores, the terminals that go on either side, and of course, color coordinating it. So we also have different tables that would identify the length of the multi-core, any cutback if you're cutting back any of the other outer shapes. And we also have an SBOM provider that outputs the labor time associated to each task. So if, for example, in your production floor, you track labor, this could serve sort of as a reference for an operator, knowing that they have a minute to complete this task. Again, here we go with another provider for twisted multi-cores. Any insulation that needs to be cut separately, we could list that, create a separate workbook page for that. And then grouping and separating our terminations into however they are processed within the production floor. So if they're separated into different cells, separated into
whether it's a bench top or hand crimping. You can divide that, as well as show graphics to show multi-crimps. So this would be very helpful, obviously showing that it's a terminal, but identifying the wires that are being crimped together at this terminal. So I talked about splices, and in particular, splice barcodes. So at Central, when we implemented Workbook, splice barcodes came in handy when we programmed the ultrasonic weld machines. So by having the barcode there, all the operator needed to do was scan the barcode, and the splice machine would automatically set itself up to weld a splice of this configuration. So then the operator essentially just had to make sure to hold the wires in place in this configuration. With insertion charts in particular, we would create, it would just be, minimal depictions of the connector. So it would be a circle with circle cavities or square with square cavities. No information on specific details of the connector or any clocking information. So an operator that didn't have much experience or was not familiar with the component could very easily insert the wires incorrectly into the connector. Say, for example, if they thought that the cavity arrangement went from A, B, and C from left to right, but they insert the wires thinking that it goes from right to left. Again, different formats. These are different providers that are being used to show the insertion of the wires into the connector. So in here, obviously, we colored in the cavities. And in this one, we're identifying the wire going into the cavity as well as where the other end of that wire will be at. Some more of those. And we also can identify different sections of the diagram. We have a diagram provider where, say for example, adding insulation, you could color code the insulation and identify where it's going to be placed on the harness. I think with that, that is pretty good recap of overview of capital workbooks. Go ahead and switch back to our presentation. So as our world becomes more electrified, the need for more connected systems grows. This results in large, more complex harnesses that wire harness manufacturers must build while still meeting cost and turnaround demands. It is time to adopt a more digital process in order to survive and grow. This digitalization can be acquired through the use of capital. It would eliminate the downstream errors through continuous data flow from the harness model through costing and to the generated work instructions. Efficiency would be improved through the automation of these processes, so no longer having to go through a manual spreadsheet or having to manually create work instructions. This would allow for more time to optimize these processes. These tools, the harness manufacturer will no longer need to fight its current tools. It will have the ability and the time to optimize the processes and compare different flows in order to determine which is the more optimal one. So as a recap, Oasis offers 3 tiers of products: Capital, Visas, and Solid Edge Electrical. These incorporate the key components of building a wire harness system involving processes, collaboration, smart data, and documentation. Our deep understanding of the industry enables us to provide the right software product and services and that allow us to solve any complex design challenge. Our team will guide you through every step of the way to ensure a successful deployment. As part of our wire harness Quick Start program, we work with you and your team on a guided pilot project. When implementing our costing and work instruction tools, we work with you and your team to create and deliver the initial pattern. We then validate it using existing designs created within Capital. This is critical in ensuring the new process is seamlessly merged within your organization's processes. Today we discussed how our Capital tool can help your organization become more efficient and stay competitive within the wire harness industry. It is important to note that the software is only as smart as the user. The proper implementation, customization, and training is key to a successful deployment, just like any other technology. OASIS provides services that are tailored to solve the challenges that companies across the world face in their day-to-day work. Our goal is to help companies bring the most advanced electrical, network, and harness technologies from concept to design through production and into service. Here is a list of the other domains that we specialize in. If you have any interest in finding out more, please reach out to myself or anyone at OASIS. I want to thank you for your time and attention today. Let us know how we can help. I invite you to save the date for our next webinar on April 11th. We will be covering how to build a library in VSys and in Capital. You can register on our website at oasissales.com. Now we will open up the floor to any questions that might have popped up during the presentation. The recording of this webinar will be shared on our YouTube channel, which you can access through our website, again, at oasissales.com. It should be available within the next week or so. If there are no other questions, I want to thank you again for your time, and I will talk to you guys next time.